Good afternoon. It gives me great pleasure to welcome all of you to the 20th Convocation of the Chennai Mathematical Institute. We are very happy to have Professor V. Srinivas as the chief guest for today's convocation. Professor Srinivas received his PhD from the University of Chicago in mathematics, and his main area of research is algebraic geometry. He joined the School of Mathematics Tata Institute of Fundamental Research in 1983, from where he has recently retired as distinguished professor. And for the past few years, he has also been the chairman of the National Board for Higher Mathematics. Professor Srinivas has had a distinguished career. He has served on the executive committee of the International Mathematical Union. He was an invited speaker at the International Congress of Mathematicians in 2010. He has, of course, received several awards, including the INSA Medal for Young Scientists, the Birla Award for Mathematical Sciences, the Swarna Jayati Fellowship, the Bhatnagar Award, the J.C. Bose Fellowship, and the World Academy of Sciences Mathematics Prize. He is a fellow of both the Indian Academy of Sciences and of the Indian National Science Academy. Welcome to CMI, Professor Srinivas. So a few words about the Institute. Of course, many of you know about the Institute, but it's worth repeating that CMI is a research institute which combines excellence in research and teaching. So the students who come to CMI come with certain expectations, and they are carefully selected, and they are among the brightest minds in the country. A large fraction of our alumni actually pursue higher studies, and several of them are distinguished academics in their own right. In recent years, CMI graduates have also taken up challenging industry positions in diverse areas. So we have many companies from sectors ranging from finance and investment to manufacturing to technology who come to CMI for campus hiring. On the academic front, we have strong research ties with leading institutions across the country and around the world. So, of course, we have numerous research projects involving the researchers in CMI and their colleagues outside. But also, CMI hosts an international research laboratory in computer science and mathematics with CNRS, the French National Center for Scientific Research. So every year, we have a number of distinguished academic visitors who come and spend shorter and longer durations, deliver seminars, teach short courses, and interact with the faculty and students. So in addition to the people here, the students get exposure to a wide variety of subjects and to people from different parts of the world. In addition to its academic activities, so CMI over the past few years has been trying to strengthen its engagement with industry and with government. In 2015, CMI set up a society called Algo Labs to interact with industry, undertake training programs, and also consulting projects in all areas which are related to the mathematical sciences. But in today's world, largely in the area of data and machine learning. Also on the government front, CMI has been working in the last couple of years with the Tamil Nadu e-governance agency to help the government make use of all the data that it has at its disposal for more effective policies and decision making. Outside of the mathematical sciences, one of the visions that Professor Seshadri, who founded CMI, had was that it should be a well-rounded university in all areas, and particularly in areas in the arts and the humanities. Seshadri, as you might know, was a very distinguished musician in his own right and a keen student of music as well. Although it is not practical for us to actually run full-fledged academic programs across all these subjects given the size and the nature of the institute, the CMI Arts Initiative was created in 2012 to promote these kind of activities and provide opportunities for students and faculty at CMI and also for people from outside CMI to come here and interact and learn from experts in the arts and the humanities. So we have been holding programs on a regular basis in areas such as literature, art, music, history, cultural heritage. Some of these are also combined with tours to nearby places like Mahabalipuram and so on. In addition, every year we host 2 international writers through a fellowship in conjunction with Sangam House Bangalore. So this provides the faculty and the students with an exposure to a much wider range of influences other than, of course, the subjects that they study here. Recently, CMI started a new center of excellence named after Dr. F.C. Kohli, the founding father of India's IT industry. So this was announced about 2.5 years ago. And the proposal is that the center will host an active visitors program with research seminars, schools, workshops in emerging areas and increase positive development on this front is that last year we have acquired a second campus space nearby, about a 10-minute walk from this campus, where we will be putting up new facilities to host these activities. We also have come into a collaboration with the Banff International Research Station in Canada, which organizes research seminars throughout the year. So CMI is now an international affiliate partner of BIRS, and from 2024, we will be hosting regular research seminars with them. And we hope to have many other such collaborations also with other academic institutions, both in India and around the world. So finally, I would like to just talk about how CMI is structured as a... So CMI is a public charitable trust, and given its size and the number of students, we do rely a lot on external support in order to sustain our activities. The National Board of Higher Mathematics, which comes under the Department of Atomic Energy, has been our major funding source from the government. But in addition to this, we get substantial support from the industry, mainly through CSR initiatives. So this comes largely from the Shriram Group companies, but also from other companies such as the Cognizant Foundation and so on. I would also like to thank, in particular, Mr. R. Tyagarajan from the Shriram Group and Mr. Lakshmi Narayanan, who's our managing trustee, for their efforts in organizing and arranging this support for CMI, without which it will be very hard to maintain the activity level that we have been able to. Finally, I would like to announce that this year we have got a large corpus grant from Mr. Prem Kumar Tatineni and his wife, Mrs. Sujata Prem Kumar, towards the activities of the FC Kohli Center. Unfortunately, they were not able to come here today, but we hope that there will be many more such enlightened individuals also who step forward to support our activities. So once again, I welcome all of you, and I declare this convocation open. Let the candidates be presented.
Sir, I have great pleasure in presenting to you 19 candidates who have successfully completed the National Undergraduate Program in Mathematics and Computer Science at the Chennai Mathematical Institute in the year 2023 and are eligible to receive the degree of Bachelor of Science Honours in Mathematics and Computer Science. So the list of students: Abhinav Sapra, Akuri Shauram, Home Rishikesh, Arindam Bhattacharya, Aryan Agarwal, Bimit Mandal, Dhrubajyoti Ghosh, Diptaksha Palit, Jessica Vipin, Makbul Manoj, Nauman Kumar, Pudipedi Udit, Narayan Shastri, Rajeshri Kanta Ghosh, Raja Tatri, Rohit Roy, Shaham Sil, Ritika Sarkar, Surya Deva Eda, Imanshu Patil,
In my capacity as the director of the Chennai Mathematical Institute, I declare that you are now admitted to the degree of the Bachelor of Science Honours in Mathematics and Computer Science, and in witness thereof, you have been presented the diplomas.
so degrees in absentia, Sir, I have great pleasure in presenting to you 13 candidates who have successfully completed the National Undergraduate Program in Mathematics and Computer Science at the Chennai Mathematical Institute in the year 2023 and are eligible to receive the degree of Bachelor of Science Honours in Mathematics and Computer Science in absentia. The list of students are Bharat Rajagopal, Hardik Kalra, Rishabh Mishra, Rishikesh Saikia, Medha Sridhar Yemili, Niranjan Kumar, Om Sai, Pranav Sanjay Gorpade, Shauvik Ghosh, Somya Dasgupta, Tejas Umesh Oak, T. Karthik Rajendran, Richik Chakrabarti.
In my capacity as the director of the Chennai Mathematical Institute, I declare that the candidates are now admitted to the degree of Bachelor of Science Honours in Mathematics and Computer Science, and in witness thereof, they have been presented the diplomas in absentia.
Sir, I have great pleasure in presenting to you three candidates who have successfully completed the National Undergraduate Program in Mathematics and Physics at the Chennai Mathematical Institute in the year 2023 and are eligible to receive the degree of Bachelor of Science Honors in Mathematics and Physics. The list of students is Shubhendu Prasad Mandal, Soham Pal, Vishnu Kadiri,
In my capacity as the director of the Chennai Mathematical Institute, I declare that you are now admitted to the degree of Bachelor of Science Honors in Mathematics and Physics, and in witness thereof, you have been presented the diplomas.
degree in absentia. Sir, I have great pleasure in presenting to you four candidates who have successfully completed the National Undergraduate Program at the Chennai Mathematical Institute in the year 2023 and are eligible to receive the degree of Bachelor of Science Honors in Mathematics and Physics in absentia. The candidates are Alok Kumar Dubey, Amitabha Ghosh, Shankhadeep Bhattacharya ji, Dipanjay Saha.
In my capacity as the director of the Chennai Mathematical Institute, I declare that the candidates are now admitted to the degree of Bachelor of Science Honors in Mathematics and Physics, and in witness thereof, you have been presented the diploma in absentia.
Sir, I have pleasure in presenting to you two candidates who have successfully completed the National Graduate Program in Mathematics at the Chennai Mathematical Institute in the year 2023 and are eligible to receive the degree of Master of Science in Mathematics. The list of students: Adrita Laha, Aniruddha Dure,
In my capacity as the director of the Chennai Mathematical Institute, I declare that you are now admitted to the degree of Master of Science in Mathematics, and in witness thereof, you have been presented the diplomas.
Degree in absentia. Sir, I have great pleasure in presenting to you 6 candidates who have successfully completed the National Graduate Program in Mathematics at the Chennai Mathematical Institute in the year 2023 and are eligible to receive the degree of Master of Science in Mathematics in absentia. The list of students: Abhishek Pradeep Kanur, Devesh Rajpal, Lakshay Modi, Pratik Roy, Saket Eram Narayanan, Tapas Paunik.
In my capacity as the director of the Chennai Mathematical Institute, I declare that the candidates are now admitted to the degree of Master of Science in Mathematics, and in witness thereof, they have been presented the diplomas in absentia.
Sir, I have great pleasure in presenting to you 13 candidates who have successfully completed the National Graduate Program at the Chennai Mathematical Institute in Computer Science in the year 2023 and are eligible to receive the degree of Master of Science in Computer Science. The list of students: Ajay Krishan NK, Ameya Anand Kamat, Chandradeep De, Gangam Reddypalli Namarada Reddy, Gurdeep Singh Sian, Rishikesh Balakrishnan, Ishan Chakrabarti, Puttalam Ramlal Srinivas, Riddhiman Datta Roy, Sagnik Dasgupta, Sagnik Datta, Samiparna Vishwas, Harish Chandramaulishwaran,
In my capacity as the director of the Chennai Mathematical Institute, I declare that you are now admitted to the degree of Master of Science in Computer Science, and in witness thereof, you have been presented the diplomas.
For degree in absentia.
1 second.
Sir,
Let them do it.
Sir, I have great pleasure in presenting to you 4 candidates who have successfully completed the National Graduate Program at the Chennai Mathematical Institute in Computer Science in the year 2023 and are eligible to receive the degree of Master of Science in Computer Science in absentia. Argadeep Ghosh, Shankar Ram Vasudevan, Shweta Bharadwaj, Tejas Shekhar Bojraj.
In my capacity as the director of the Chennai Mathematical Institute, I declare that the candidates are now admitted to the degree of Master of Science in Computer Science, and in witness thereof, they have been presented the diplomas in absentia.
Data Science. Sir, I have great pleasure in presenting to you 35 candidates who have successfully completed the National Graduate Program at the Chennai Mathematical Institute in Data Science in the year 2023 and are eligible to receive the degree of Master of Science in Data Science. Abhishek Mishra, Aman Kumar, Ananya Sankar Narayanan, Anjali Pugalia, Aniket Santra, Ankush De, Ashutosh Maurya, Abhik Das, Ayush Srivastav, Deepti Kumawat, दोना घोष, कृष्णा गुप्ता, कुमार प्रियंक, मोहम्मद हशीम एम, मौमी रॉय, नहेली भट्टाचार्य, नेहा, नेवेता एनजी, प्रज्ञा जायसवाल, प्रशांत बाजपेयी, राजस शशांक वैद्य, रक्तिम दे, रविला भरत कुमार, ऋषिका तिब्रेवाल, रीतिरूपा दे, रोहन मिलिंद धर्माधिकारी, शरीउल हसन हाशमी, श्रमना कुई, श्याम कृष्ण पी, सिंजनी सिन्हा, सोहम पैने, श्रीजीत साहा, सुचेता झुंझुनवाला, Ujjwal Saxena, Ved Prakash.
In my capacity as the director of the Chennai Mathematical Institute, I declare that you are now admitted to the degree of Master of Science in Data Science, and in witness thereof, you have been presented the diplomas.
Degree in absentia. Sir, I have great pleasure in presenting to you 10 candidates who have successfully completed the National Graduate Program at the Chennai Mathematical Institute in Data Science in the year 2023 and are eligible to receive the degree of Master of Science in Data Science in absentia. Aditya Anand Kumar, Agnija Ashrita, Atul Prakash, Dhruvi Mohan Chauhan, Ishan Singh, Jaisuryan CS, Meghna Mandal, Riva Malik, Shreyansh Rastogi, Soham Biswas.
In my capacity as the director of the Chennai Mathematical Institute, I declare that the candidates are now admitted to the degree of Master of Science in Data Science, and in witness thereof, they have been presented the diplomas in absentia.
Sir, I have great pleasure in presenting to you one candidate who has successfully completed the degree of Doctor of Philosophy in Mathematics at the Chennai Mathematical Institute in the year 2023 and is eligible to receive the degree of Doctor of Philosophy in Mathematics. Plavan Das.
In my capacity as the director of the Chennai Mathematical Institute, I declare that you are now admitted to the degree of the Doctor of Philosophy in Mathematics, and in witness thereof, you have been presented the diploma.
Sir, I have great pleasure in presenting to you one candidate who has successfully completed the degree of Doctor of Philosophy in Mathematics at the Chennai Mathematical Institute in the year 2023 and is eligible to receive his degree of Doctor of Philosophy in Mathematics in absentia. Dharam Veer.
In my capacity as the director of the Chennai Mathematical Institute, I declare that the candidate is now admitted to the degree of Doctor of Philosophy in Mathematics, and in witness thereof, he has been presented the diploma in absentia.
Sir, I have great pleasure in presenting to you one candidate who has successfully completed the degree of Doctor of Philosophy in Computer Science at the Chennai Mathematical Institute in the year 2023 and is eligible to receive the degree of Doctor of Philosophy in Computer Science in absentia. Pranjal Datta.
In my capacity as the director of the Chennai Mathematical Institute, I declare that the candidate is now admitted to the degree of Doctor of Philosophy in Computer Science, and in witness thereof, he has been presented the diploma in absentia.
Sir, I have great pleasure in presenting to you two candidates who have successfully completed the degree of Doctor of Philosophy in Physics at the Chennai Mathematical Institute in the year 2023 and are eligible to receive the degree of Doctor of Philosophy in Physics in absentia. Ramadas N. Saurav Roy Chowdhury.
In my capacity as the director of the Chennai Mathematical Institute, I declare that the candidates are now admitted to the degree of Doctor of Philosophy in Physics, and in witness thereof, they have been presented the diplomas in absentia. So we have one more candidate who is receiving the degree of BSc Honours in Mathematics and Computer Science today, Himanshu Patil. I have to read out the gospel truth. In my capacity as the director of the Chennai Mathematical Institute, I declare that you are now admitted to the degree of Bachelor of Science Honours in Mathematics and Computer Science. In witness thereof, you have been presented the diploma. So we now come to the special awards. So we have a special award for women students instituted by Mr. Arun Dugal, who is one of the members of the CMI Trust. So there are two awards. There's the Rita Dugal Award for the best student, female student outgoing in the Master of Science MSc Mathematics program, and the Arun Dugal Award for the best undergraduate student, girl student in the mathematics program. In addition, for each discipline, CMI has a gold medal of excellence for the best outgoing student. These awards were initially instituted by Professor K.R. Nagarajan and by Professor Gauri Vishwanathan, and also supported by Bajaj Alliance and also CMI itself. So I will now request Professor K.V. Subramaniam to read out the names of the recipients.
Yeah. The award winner for the Arun Dugal Award, Ritika Sarkar. The winner of the Rita Dugal Award is Adrita Laha. winner of the CMI Gold Medal of Excellences, CMI Gold Medal of Excellence in BSc Honors in Mathematics and Computer Science, Bimit Pondal. The CMI Gold Medal of Excellence, BSc Honors in Mathematics and Physics, Soham Pal. The CMI Gold Medal of Excellence, MSc Mathematics, is Adrita Laha. Adrita Laha. CMI Gold Medal of Excellence, MSc in Computer Science, goes to Rishikesh Balakrishnan. CMI Gold Medal of Excellence, MSc Data Sciences, goes to Prashant Bajpai.
Thank you. Congratulations to all of you. Thank you. I now invite Professor Srinivas to deliver the convocation address.
Well, I'd like to thank Madhavan and the CMI authorities for inviting me to be here on this occasion and make this presentation. In fact, when Madhavan first talked to me, he explained to me that things work a little differently at CMI. What is required is a mathematics lecture of some kind, which is sort of accessible to people to the extent that it's possible to make it accessible. So I said, okay. If it had been the normal kind of convocation address one is used to, where I'm supposed to get up here and give you life experience things, gyan, and tell you, do this and that, inspiring. I'm the wrong person for that. I can do mathematics. I can tell you a little bit about mathematics, and that's why you're here. CMI is a very special place. It's for those, I feel, who think like I do about mathematics. What you pay homage to is the mathematics, so to speak, whatever that means. Okay. So I'm talking on this topic, what are the Bloch-Beilinson conjectures? Conjecture means it's something we don't know. I think that's the right sort of thing to do, talking to young people who are about to start out a career in mathematics and who are very smart. You have to put something really challenging, hard, interesting in front of them and say, go there and do it. Show us how it's done. We tried, we did what we could, we've stopped here. Now it's up to you to take our subject forward. This topic is very much like that. I'll try and convey something of the flavor to you. Okay. Let's start with two formulae which appear, for example, in the writings of Srinivas Ramanujam. This is meant for the general audience part. The math guys, of course, already know all this stuff. These are two strange looking formulae. 1 plus 2 plus 3 plus 4 equal to minus 1 over 12. And the second one is 1 squared plus 2 squared plus 3 squared plus 4 squared is 0. So initially when Ramanujam tried to present these formulae to some people, people thought, this is a strange guy, get him out of there, type of thing. Anyway, we now know, of course, that, and many of you in the audience, I'm sure many of the CMI students know, what is the explanation for these formulae. There's something called the zeta function. Zeta s is summation n equal to 1 to infinity, 1 upon n to the power s. I think of s as a complex variable, so the real part is bigger than 1. If you don't like complex variables, take real variables. 1 over n to the p, it was the way when I was an undergraduate student. Okay, what Riemann showed is that s minus 1 times zeta s extends to an entire holomorphic function, a function holomorphic in the whole complex plane. And it satisfies a functional equation. You take this zeta s, multiply it by this factor involving this other function gamma and pi, some power of pi, and then take s goes to 1 minus s, and you get back the same function, right? A so-called functional equation. So this is the sort of thing, for example, Ramanujam was a genius at, and I'm sure many of you people here sitting in the rows here are pretty good at these things too. Okay, so what is the gamma which I use? Gamma is this integral 0 to infinity, x power s minus 1, e to the power minus x dx. And this makes sense only when s is positive basically. But then it satisfies this functional equation, and using the functional equation, if I want to compute the value at s, it's enough to understand the value at s plus 1, and then using it again, it's enough to understand s plus 2, s plus 3. So whichever negative or other value I have, I can propagate it out to the positive side, compute it, and come back using the one. So you can extend it to the whole plane with some singularities, because you'll have this s there, and it'll go to the other side, you'll divide, things will happen. So this is a generalization of the factorial, which was invented by Euler, but Ramanujam also certainly knew this function in his role. And using this, one is able to show things like this. Zeta of minus 1 is minus 1 over 12, and zeta of minus 2 is 0. So why have I brought in these negative numbers? Because if you go back to the original formula there, zeta s was summation 1 upon n power s. But if I make s equals minus 1, 1 upon n to the power minus 1 is another way of just writing n in the numerator. So this series here is, so to speak, zeta of minus 1 if I can make sense of it. And using the functional equation, I can make sense of it. That's the point. That's why the functional equation tells you something. So similarly, the other one is zeta of minus 2. So there are these two formulae, and in fact, more generally, zeta at any negative even integer is 0, and zeta at a negative odd integer has a formula as minus b2m divided by 2m, where b's, these numbers b's are certain rational numbers which occur in this series expansion. So this is a formula which is again known to Euler, and I believe Ramanujam was certainly familiar with this as well. So by the way, here the zeta has these zeros. Some of you might have vaguely heard there's something called Riemann hypothesis, a famous problem, and it talks about the zeros of the zeta function. Well, it's not these zeros. These are what we call the trivial zeros. So the Riemann hypothesis talks about the other zeros, if any. And there are infinitely many of them, and they are the so-called non-trivial zeros of the zeta. And the hypothesis is about those. Anyway, if someone is interested later on, I can tell you more about it, for those who don't already know. Actually, in this audience, there might be people here who know much more about the zeta function than I do. But anyway, it doesn't matter. Let me carry on. The Bloch-Beilinson conjectures, the topic of my lecture, and refinements, this is really more to the point. Bloch-Kato, down the line, if you want to work on research, probably Bloch-Kato will be more what you might do. These try to relate two different kinds of data coming from different parts of the subject, which are associated to what are called algebraic varieties, which are defined over algebraic number fields. So these things in italics are some technical terms. I'll have to try and explain a little bit, at least give you the flavor of what they're about. And whatever these objects are, these algebraic varieties defined over number fields, associated to them, we have two different kinds of data, and then the conjectures try to relate those two different kinds of data. That's what the problems are about. And these are very much open problems. I do notice a few people in the audience who heard a version of this talk before. Don't worry, there's been zero progress since you last heard it. So it's still as open as it was the last time you heard it. But maybe with some of the young chaps from CMI here going out there, young women and men, doing really good work, some of you will make some progress and break some holes in this huge wall where we have no idea what to do next. Anyway, I'll get to that eventually. Okay, so what are the two types of data? I said associated to these varieties, there are two different types of invariants. One are orders of vanishing and special values of what are called zeta functions, like the Riemann zeta function, and like those formulae which I wrote down, and other generalizations called L functions. And the second type of invariants are things called higher Chow groups and so on, which are defined using algebraic geometry, which is really my subject, and algebraic K-theory, another sort of advanced branch of mathematics. And whatever these conjectures are, they're supposed to explain formulae of the type which we saw earlier. The zeta function is some of the case where it's the simplest field, the simplest things, just the space is a point, and so on. Already you have Riemann hypothesis, you have all sorts of unknown things. So this is talking about any space, any dimension, they're very out there sort of statements. Okay. What is the reason I myself have been interested in such things? I don't primarily work in this mathematics, I work in algebraic geometry, but let me state something in algebra which I hope will be understandable to many people. And these conjectures have something to do with it. That's the surprising thing. So let A, B, C be three complex numbers. This symbol C stands for the complex number. And an easy fact that if you have a polynomial in three variables, f of x, y, z, and it happens to vanish at the point with coordinates ABC, that is f of ABC is 0, then I can rewrite the polynomial as x minus a times some polynomial plus y minus b times a polynomial plus z minus c times a polynomial. I can write it as a polynomial linear combination of the three linear polynomials x minus a, y minus b, z minus c. This is a pretty obvious fact. Just expand the polynomial f of x, y, z as a Taylor series around the point ABC, you'll get a bunch of terms. There are only finitely many terms. It's a polynomial. After a while, all the derivatives are 0. Or put a different way, make a substitution. X equals a plus u, y equals b plus v, z equals c plus w. Write it out in the variables u, v, w. Every term is divisible by 1 of u, v, w. Substitute back, it's sort of obvious. But now, suppose my point ABC, the triple, happens to satisfy this equation. A to the power 37 plus b to the power 37 is equal to c to the power 37. So that means this point ABC also lies on the surface in 3 space defined by this equation. x37 plus y37 minus z37 equals 0. So this is a specific polynomial which vanishes at ABC. So the algebra problem I want to ask is the following. For which triples ABC can I find two other polynomials, g and h, so that any polynomial f of x, y, z satisfying f of ABC equals 0 can be written as this x37 plus y37 minus z37 times p plus the combination of the other two. In other words, instead of the three linear polynomials, I want to take one of them to be this complicated polynomial, and then I'm allowed to choose the other two as I like, depending on the first one. Can you solve this or not? Of course, it's a logical question. Either it has a yes or no answer. The obvious guess, if somebody asks you, they'll say, impossible. It can never be done. That's the answer. But the surprising thing is, it's not. Geometrically, if you want to think in terms of geometry, I have those two other functions, g and h, two functions together the zeros of two common zeros of two functions should define a curve in three-dimensional space. That curve intersects the first surface exactly in ABC and with no other solutions. That's what the geometric problem means. So again, in geometry, this is this very high degree equation. I'm taking two other high degree equations. I'll expect lots and lots of solutions, but I want to get only one. The point ABC I started with, and no other extraneous thing. That's what the geometric meaning is. It looks highly unlikely. And I just took 37 to make this concrete. In fact, for this talk, I should have changed it to 2023, right? And we can ask it for any power. And in the end of the talk, I'll try to indicate what is the solution. It's not the empty set. It's an interesting set. It's not at all obvious. And these conjectures have something to do with it. Okay. Now, let me try to tell you a bit about what these conjectures are. I had all those technical words. I'll try to spend some time explaining what the words mean. I hope I can convey something of the flavor. Okay? It's not very easy mathematics. This is hard, unknown mathematics, so it's a bit tough to convey, but I'm trying to motivate the young people to do it. Okay. So basic objects of study in algebraic geometry are what are called algebraic varieties. And there are two most important types, what are called affine varieties and another type called projective varieties. Whatever they are defined as solution sets of finite systems of polynomial equations. Earlier I took one polynomial equation, you can have a system of equations. And whatever these projective varieties are, they are things where the equations have to be homogeneous. So I'll try to illustrate that a little more. I'll explain that a bit more. For example, I took this equation, x37 plus y37 minus z37 equals 0. Right? That defines a surface in 3 space. And in fact, it's a homogeneous polynomial. Every term has degree 37, the same degree. That's what homogeneous means. That means if you have a solution, any proportional vector is also a solution. So the space of solutions is naturally a space of lines in 3-dimensional space. Lines through the origin. So I'm just saying, therefore, since I can think of the solutions of this equation as a set of lines, I can think of it as defining a set inside the space of all lines, which is something called the plane, projective plane. The projective plane is the space of lines in a 3-dimensional space. And so I claim the same equation, this homogeneous equation, simultaneously defines a surface in 3 space and a curve in the space of lines. So the picture you should have is this, taken from a standard textbook. It's a nice picture. Inside 3 space, I have some homogeneous equation. It defines a solution surface. The surface consists of a bunch of lines. So each line inside 3 space, I choose a point in a space, so there's a space parameterizing the lines. So how should I think of this space? For example, if I was in Euclidean space and I think of lines through the origin, Euclidean 3 space, I could think of a sphere of very large radius, right? And a line through the origin will hit the sphere, but it will hit it in 2 different points, and I want to count each line only once. So I should be able to take the sphere, take 2 opposite points, identify them together, and whatever the quotient space is, that should be the space parameterizing the lines, right? That's called the real projective plane, this space, the sphere with this identification. But I'm over complex numbers, so it's more tricky than that. Really complex 3 space is real 6 space. So instead of the 3 sphere, I should be taking the 5 sphere inside 6 space. And if you think of a complex line and ask how does it intersect, it will intersect in a circle. So really I have the 5-dimensional sphere. I've got a bunch of circles which move around it, and I take the quotient space, which is some 4-dimensional space. That's the complex projective plane. The space of lines complex lines in a 3-dimensional space. It's a plane in the complex sense. So the complex dimension is 2, the real dimension is 4. Right? It's the 5 sphere with quotienting by a bunch of circles. And then in higher dimensions, you can imagine getting more and more mind-boggling if you're really trying to see the picture. Anyway, that's the space. Okay. Well, for example, very quickly, let me give you a quick thing about projective geometry. You might have heard something that in the projective plane, there are no parallel lines. Any 2 lines meet. So how do we understand that from this picture? I claim the picture actually explains that. If you took a line in the plane, projective plane here, that's like a bunch of lines in 3 space. So it's a plane in 3 space through the origin. So suppose I take 2 such lines in the projective plane. That's 2 planes in 3 space through the origin. But two planes in a three-dimensional vector space, you have two-dimensional subspace. The intersection is dimension 1, at least, right? Or they might be the same. The intersection is non-zero, and it's a vector space. So it's a positive dimension for the theory of dimension. Therefore, there must be a common line in both of them. That means the original lines in the projective plane have a common point. So projective space has this nice property that there are no missing things. There's no stuff going off to infinity. There's no parallel things. That's why it's better for algebraic geometry. Okay, anyway, just to give you a flavor of how to think about these things. Right. Okay. This is really meant for the general audience. If you didn't follow anything else about projective geometry, do take a look at this website, www.imaginary.org, and look at the things there. These people try to show that you can produce very interesting artwork using the pictures which you get from real algebraic surfaces. Take surfaces in 3 space, look at the solutions over real numbers by nicely choosing, for example, this equation. 60 times x squared plus y squared times z raised to 4 is equal to 60 minus x squared minus y squared minus z squared to the power 3. It produces this nice top, looking like a top. They have a huge number of things. So they produce all sorts of things for the public. This Imaginary is a traveling exhibition. And there's a website. So for those who don't get anything else from the talk, this might be fun for you to look at. If you need something for some presentation somewhere, you need a cool looking figure, go look at these fellows, copy something from there. Okay. Now coming back to mathematics, I'm dealing with algebraic varieties over the complex number field, but which are what are called defined over an algebraic number field. That was the second thing in italics in my earlier slide. And I'll in fact only take the rational numbers in this talk. But number fields are things like rational numbers with finitely many things adjoined, some solutions. What that means is that, remember, an algebraic variety is a solution space of a system of polynomial equations. Those equations have some coefficients. Those coefficients, to start with, might be complex numbers, but I can restrict myself to the situation where all the coefficients are integers, are rational numbers or integers. That's the situation of interest to me. That's what's defined over the rational numbers. That Fermat surface I took, x37 plus y37 minus z37 equal to 0, was of that type. The coefficients are zeros or ones. If I take a polynomial of degree 37, 3 variables, it has huge number of coefficients. I wrote only 3 terms. What it means, every other term is 0, right? So, but 0 is certainly okay. It's an integer. And the others, 1, 1, 1 are okay, right? So, such things are, well, if you have such algebraic varieties, instead of looking at all complex solutions which have a geometry, I can look at the special solutions where the coordinates are themselves integers or rational numbers. Then I bring in number theory, right? So, but one of the important themes which we have learned in modern number theory is that the geometry is one of the inputs. Even if you're interested only in the number theory, you have to understand the geometry first. Only then put the number theory into that afterwards, and then you can proceed. Okay. And geometry comes in all sorts of non-obvious ways, somehow. That's the point. Anyway, so this is, I'm afraid, a little advanced for the people, but I have to say it because it will be correct. An algebraic variety X in the affine space or projective space is called non-singular if it's what's called a differentiable manifold, in the sense that I can do calculus and differential geometry on it. So those of you who have taken more advanced courses, certainly the MSc people, and maybe even do you do differential geometry in your undergraduate program? Have you seen a bit? Okay. You will, if you do any more mathematics very soon, you will encounter it, and I'm sure the masters people know that. So it's a space on which it's possible to do calculus, basically. That's what a differentiable manifold is. And in fact, we have to not only do calculus and differential geometry, we have to do complex analysis and other things on the space, on our space. Anyway, whatever they are. So in the projective case, it turns out these are what are called compact-oriented manifolds of topological dimension twice the algebraic dimension. Remember that the number is always double. Right? That's an important thing to keep track of. Doesn't matter, these are words. If you have not seen it, it's not so important. But to give correct statements, I have to put in these technical words. Whatever it is. But you should take away this message. Topology of the space does come into the play. If you want to understand number theory, you have to understand geometry, you have to understand differential geometry, you have to understand topology. All of those things are going to influence number 3 in the end. Something like Andrew Weil's, proof of Fermat's last theorem, he used everything else which was developed before, right? So that's the style in which, and a lot of things have been developed since then. And if you want to tackle these conjectures, you will have to use all of those things also probably. Anyway, and tell us how it's done. Right. Now let X be one of these non-singular complex algebraic varieties, and then it's possible to associate to it certain groups depending on 2 parameters P and N. P and N are non-negative parameters, integer parameters. And these, whatever they are, they reflect the properties of the geometry of the space X. And these are called higher Chow groups and are defined by Bloch and used in formulating these Bloch-Beilinson conjectures. So I'll tell you a little bit more about these, but I want to say these are one of the players in the game. These things, Chow P, X, N, with 2 parameters P and N. So what are they? I can't give you a proper definition here, it's too hard. But a generator of this Chow P Xn is some sort of finite formal sum of families of parameterized families of subvarieties inside X. So what you do is you take X cross N, the n-dimensional space. So think of these n coordinates as extra parameters. So remember there are 2 indices, P and N. So this N tells me how many parameters there are. Then you take essentially P equations inside the product space and take the zeros. So I'll get some family of varieties. For each value of the parameter, I get something inside X. Just to fix ideas, suppose X is a surface, and suppose N is 1, and suppose P is 2, just to fix ideas. Okay? So X is a surface, N is 1. So X cross C is 3-dimensional. Then P is 2, so I take 2 equations in the 3-dimensional thing. I'll get a curve inside that 3-dimensional thing. I have 1 parameter because N was 1. So for each value of the parameter, it will intersect the curve in finitely many points in some fashion. And as I vary the parameter value, my points will move around. Maybe the points will have multiplicities. They'll do some sort of dynamics. That's the sort of object in that case. And similar higher dimensional things are there with more parameters and higher dimensional spaces inside X. Okay. So there are certain kind of geometric objects you can write down. And there is a chain complex which you can write down in the sense of homological algebra. In degree n, P is fixed, n is varying as you try to write down the chain complex. And in degree n, you use subvarieties of this x cross Cn, but then the sort of boundaries and so on. There are some further homological things, and then you construct the homology. So for the masters, people who might have taken a course in homology, it's like what you do in topology, but something done purely using algebraic geometry. Okay, doesn't matter whatever they are. They are some things of a geometric nature coming from the space X. Now, for n equals 0, we're just considering subvarieties of the space X itself. There are no parameters. And for the boundaries coming from n equal to 1 are some sort of what is called homotopy. You have 1 parameter, so you have 2, if you have 2 things inside X, I can ask when can I deform one into the other with a single parameter family. That's like what in topology you will call homotopy. Deform one geometric shape into another smoothly. This is a similar thing but higher dimensional and algebraic. Okay. Right. The space Chow P X0 without the parameters were defined earlier and they were called Chow groups in the literature. So Bloch, who defined the thing with the parameters, called them higher Chow groups. So these are one of the players. But that still doesn't do it. This works only over complex numbers. I haven't brought number theory in yet. That still comes in here. There is a way of defining a subgroup of this called the group of integral elements, whatever it is, and it was defined by the other person, Beilinson. I mentioned 2 names, Bloch and Beilinson. Bloch defined the higher Chow groups, the geometry part. Beilinson showed how to construct in principle these things inside this with the integers put here. Even to make sense of this Beilinson's definition, you have to assume certain conjectures on what's called arithmetic resolution of singularities. That's a famous thing where the first non-trivial case was done by an Indian mathematician, Abhyankar. That's one reason I brought this. I wanted to mention Abhyankar made the first serious contribution here. Abhyankar's work was in the 60s maybe or 70s. Somebody in 2018 or 19 has managed to do the next case. That's about it, the progress. We haven't progressed beyond in that realm. But dimension 2 Abhyankar did. Dimension 3 has been done after close to 50 years. So maybe higher dimensions now we might see some progress. It's possible. Anyway, that's one thing, the geometric thing. But then also one has to use something called algebraic K-theory. This is a complete black box now. I can't tell you anything. But doesn't matter. That's another higher dimensional geometric theory using algebraic topology, using various things. That too is required in order to define this. It doesn't matter. It's, I'm just not able to tell you what it is in a talk like this. For your kind of students, I think if you gave me 3 days, I'll be able to give you lectures, and then morning till evening we'll lecture every day for 3 days, and then by the end of that you'll have an idea about algebraic K. I wrote a book on it, so I should be able to do it. Anyway, so then the first conjecture is that the Chow groups with this Z here are finitely generated. The original ones are supposed to be finitely generated, and then Bloch said, well, these higher ones should be as well. That's conjecture one. This is not yet the Bloch-Beilinson conjecture. Finite generation is the first thing before you can even formulate the conjecture. What's the background here? The Chow group thing is somewhat classical. It's folklore. There's no name we can really attach to it. But the only case we know is something like 100 years old. It's something like it's called the Mordell-Weil theorem for abelian varieties. Some of you who studied some number theory might have heard about this. The group of points on an abelian variety or an elliptic curve is finitely generated. Essentially, that's the only result we know in this direction. Everything else, there are many things you can write down, but they're really the same thing in disguise and then change variables and bury it in the middle of something else. You haven't done anything non-trivial. The only non-trivial result is this. And it's close to 100 years old. We haven't progressed beyond it. People want to see progress. I mean, it may look like very little is directly understandable in this talk to you. What I'm trying to put here for the young people, this is all stuff for the future. There are a huge number of questions here. We don't know many things. That's the sort of thing which you people should be thinking about and trying to make progress. It's really, that's why I chose this particular topic. It's technically kind of difficult, but that's what you people have to wrestle with and make progress. That's what, what we want to see. Finite generation is not known in any non-trivial case where n is greater than 0, where you really have a genuine higher Chow group in the sense of Bloch, except when x is of dimension 0, the space is a point. Finite generation is known there, but it boils down to the famous theorem of M.S. Raghunathan on finite generation of the cohomology of arithmetic groups. Raghunathan was supposed to be one of the stars of our previous mathematics generation, one of the youngest ICM speakers from India. He proved that that takes care of the finite generation for x equals a point. And we want it for x of any dimension. So the finite generation, that's the open question. But, that's the sort of challenge you people should be addressing tomorrow. Okay. Bloch-Beilinson will not only take finite generation, it will tell you a formula for the rank, for how many generators you need, in terms of something else called L functions. That's what the conjecture. We don't know finite generation at all. In most of the cases, in spite of that, they want to go ahead and predict, not only is it finitely generated, I'll tell you how many generators there is from some other number theory data. That's the nature of the problem. Okay? And in the very special case where x is an elliptic curve, dimension x is 1, it's a very special type of curve, p is 1 and n is 0. This is the $1 million problem, the Birch-Swinnerton-Dyer conjecture. Partial progress on this, people have won the field medal. So, whatever conjecture I'm talking about, a very, very, very special case will already get you $1 million, you can solve it. Okay, so this is a really challenging, ambitious sort of problem. Anyway, that's why I like to put down this comment, to boldly go where no mathematician has gone before. This is something which speaks to a certain generation. I can see the older members in the audience are familiar with the Star Trek TV program, and James T. Kirk, who talks about space being the final frontier and so on. So this is like that in mathematics. Okay? Right. So what are L functions? The other thing which I said are going to be used in order to get the rank. So the basic example is zeta, but instead of writing zeta in terms of this series, we have to write zeta in terms of this product. Product over prime numbers of 1 over 1 minus 1 by p power s. Have people seen this formula? I think many of the students will know this, right? Okay, good. So all the CMI students know this. So this explains why this zeta function, if you take log of zeta, the singularities of log of zeta come in particular from the zeros of zeta. And on the other hand, log on the other side makes this into a summation over prime numbers. That's why the zeros of zeta function are important in counting the number of primes. That's why Riemann hypothesis has something to do with the distribution of primes, because of this formula. For example, there are infinitely many primes because the series summation 1 upon n is divergent. Put s equals 1. This side is divergent. On the other hand, if there are only finitely many primes, this would be obviously convergent, and then I expand out finitely many terms, it's convergent. So that's a contradiction. So there must be infinitely many terms, right? It looks like a very fancy way to prove something which you know in obvious ways. But if I want to prove the infinitely many primes congruent to 3 mod 7, there's no other method except to do something like this. L functions were invented to solve those kinds of questions. Anyway, the general L function I need to consider will similarly be defined in this fashion. There will be product over primes P of LPS for some functions LPS. So what are these LPs? Let me give an example first. Let's take X, a so-called elliptic curve over Q, and it's defined by this type of polynomial equation. Y squared minus a cubic polynomial in X where A, B are integers. Right? And there's a condition that this cubic has 3 different roots. There are no repeated roots. So now, because A, B were integers, I can just substitute values of X and Y from 0 to P minus 1 and just calculate the value of fxy and ask, is it divisible by the prime number P or not? So in other words, I'm computing mod P, how many solutions the same equation has. That would be the way to say it. Now, if I just take the remainders, they are P squared values, right? Because they are P values of X and P values of Y. There are 2 variables X and Y. They are P squared values of the remainder, but they are P remainders. So if all the remainders are equally likely, each one must occur P times, right? So of course there might be some deviation. So let's count this deviation, AP, P which is the expected number and NP the actual number of solutions. Okay? So this is a simple enough thing. Then what you do is you write down this function. P is the product of good primes of 1 by 1 minus this number AP divided by P power S plus P divided by P power S squared. And then there are some factors of bad primes. I won't say what they are. But whatever bad prime is, I'll tell you that P divides 6 times 4a cubed plus 27b squared. Ask, what is this 4a cubed plus 27b squared? This is the condition saying this is not 0, is the condition that that cubic polynomial x cubed plus ax plus b has distinct roots, which was the condition that it's an elliptic curve. So P does not divide means even mod P it has distinct roots. So even mod P you got an elliptic curve. And that's really the condition. And algebraic geometry will in general tell me there are only finitely many primes where things go wrong. If things are okay over rational numbers, then mod P for all except finitely many primes, it will look, many properties will be similar to what you got over the rational numbers. Here it's an explicit formula. P dividing this, if P is bad, then P divides this. Okay? And there's some formula for those LPs. Okay, great. It's a formula. I just wrote down and said, this is the L function. Okay, it looks like some fantastic thing. If I take you give you the next one, how are you going to write with that one down? What will you do there? Right? It's not obvious. So you want a more conceptual way of thinking about this. This is fine for explicit, but this is not the reason. It's the general definition is less explicit but more conceptual. So I'll try to say something about that because very nice mathematics comes in there also. It turns out that basically you want to write down an L function associated to each of what's called the cohomologies of the projective variety X defined over Q. So remember I told you I started with the variety X which happened to be defined over Q, but it was a non-singular projective variety. So I also said once it's a non-singular projective variety, whatever that is, I can do differential geometry, I can do calculus, but I can also do algebraic topology. I can do things like homotopy theory. I can compute the cohomology groups of the space, of the underlying topological space. For example, an elliptic curve, one knows topologically is just a standard torus, right? So it has 2 cycles, right? The torus, the circle goes this way and that way, the standard pictures you see, right? And similarly, you can have a sphere with many handles, and then you have the usual pictures of the kind of cycles you can write down on spheres. So those things are examples of things coming from topology. So I have the cohomology groups which measure something like the higher dimensional holes of the space. and the L functions are somehow associated to those cohomologies. That's the claim. And at these good primes, I'll be able to write a sort of formula. LP of HIXS will be some polynomial FPT evaluated at t equals 1 over p power s. So let's just go back to the formula where we had this. So here what I did, okay, let's go even further back. Let's go to the Riemann zeta function. Here I just take the polynomial 1 upon 1 minus t and then put t equals 1 by p power s. Then I got this expression. Okay? 1 upon 1 minus t and then t equals 1 over p power s, I got this. So in the elliptic curve case, 1 minus apt plus p times t squared. If I wrote that quadratic polynomial in t and then substitute to t equals 1 over p power s, I'll get this. Okay. So in general, the formula will look something like that. Well, I made a mistake here. I should have written this 1 upon fp of 1 over, there's a 1 upon missing there in the slide. Right? It comes in the denominator always. Well, it's a point of view. Sometimes, depending on it, I can think of it as a numerator by 1. Okay, it doesn't matter. Anyway, it's all very vague and sort of abstract here. But whatever this formula is, it's based on the so-called Weyl-Riemann hypothesis, which was proved by Deligne. And Deligne won the Fields Medal, among other things, for this thing. And he used it to prove the Ramanujan tau function conjecture. Many of you might have heard about that at least. Tau n is, tau of p is bounded by 2p to the 11 by 2, right? There's some formula conjectured by Ramanujan. This was proved by Deligne. And as part of whatever machinery he developed, he gave a way of computing this polynomial fp. That's the point. It's the same sort of polynomial which appears even in the Ramanujan business. There it will be a quadratic polynomial, but whatever it is, some polynomial. So then Serre in 1971 predicted that these L functions, which I sort of gave some idea of the definition, satisfy a functional equation similar to the Riemann zeta function, relating the value at s with the value at I plus 1 minus s, where I is this ith cohomology. Okay. Serre also gave a formula for computing the simple function and gave the full information, but for this talk it's enough that you understand Serre conjecture something like this. If somebody really wants to know, I have Serre's paper downloaded on my laptop, I'll be happy to share it. For the zeroth cohomology, one just gets back to the Riemann zeta function, and for the top degree cohomology, where d is the dimension, one gets the zeta function with a shift. So there's no new information. The new L functions are the other cohomologies. That's why for an elliptic curve, there was H0, H1, H2, and H0 and H2 are sort of obvious, zeta. So H1 is the interesting L function. What about this Serre conjecture? Do we know it in some cases? We do in a few situations. Basically, this is what Wiles proved the Serre conjecture for L of H1 of an elliptic curve. That is the main theorem of Wiles. And then the other stuff, the Fermat last theorem and so on, are corollaries. This is the main theorem, that there is a functional equation for the L function. The L function is modular, is the way they would say it. A modular function is a function satisfying certain types of modular functional equations. So saying the L function satisfies the functional equation is this, people say that loosely, they'll just say the L function is modular. That's what, when they say the L function is modular, they mean the L function satisfies this sort of functional equation. Now, let me get to the actual conjectures, the Bloch-Berezin conjectures. Let X be one of these objects for which I have these various things I can define. The conjectures try to describe the behavior of the L function of each of the cohomologies near integer values of S in terms of certain higher Chow groups. I'll be more specific in a second. But if I want to understand this near integer values, I only need to understand half of the values because of the functional equation. Values on one side are related to values on the other side. And remember, even for the zeta function, we got very nice formulae for the negative numbers. For the positive numbers, there are no simple formula. For the positive even numbers, there are some formula with pi and so on. Positive odd numbers are all sorts of open questions. Zeta of 3, we know is irrational. We do not know it's transcendental. Things like that. But the negative numbers, lots of nice things are there. So similarly here, it's better to look at the things on the negative side. That's what people found. And the first conjecture says, if m less than or equal to I by 2 is an integer, then the order of vanishing of hi at s equals m is the rank of this particular arithmetic higher chow group. The indices are not the same. You have to figure out, part of the conjecture was to figure out what's the correct thing to put here. And this is what they found. And the second part is, if n is this order of vanishing, there's in fact, you take that group which is supposed to have that rank, mod out its what's called its torsion, it sits as a lattice in a Euclidean space, in a natural way of that dimension. The image is a discrete lattice, and the volume of the quotient is the leading term in the Taylor expansion of the L function at that point. That's also part of the conjecture. So the conjecture predicts the rank, and it predicts the leading term of the Taylor expansion. I won't say what is regulator. I mean, many things I have not explained. Regulator is even one more thing to explain, but it's a sort of determinant whose entries are integrals of some kind of differentials over those higher Chow cycles which we constructed. So if you want to integrate something, you have to have a space or a domain over which you integrate, and the domain over which you integrate is this higher Chow cycle which is coming from the geometry, algebraic geometry. That's the correct place on which to integrate. Okay? That's what the conjecture predicts. And m less than or I plus 1 by 2 means this twist here is actually strictly positive. That means this is a so-called higher Chow group, a new object. But there's one case left over. If I is odd and I take I plus 1 by 2, that's an integer. This involves the classical Chow groups, and in fact it will be sort of the middle of the strip giving the functional equation. If you've ever looked at the Riemann zeta function, and you know what the Riemann hypothesis is, it talks about the center of the critical strip. So similarly, this is the center of a suitable critical strip, that particular place. So what you're forced to do then, you can break up this rank. So I have this Chow m x z, right? This is some finitely generated thing according to conjecture. I'll break the rank into two parts. The part where I can see it in topology, I take the image in cohomology and I'll get some image there and it'll have some rank, whatever it is. And I have the other stuff which I don't see at all, the so-called kernel, the relations. So break the rank up as a sum of two terms. The rank of the stuff homologous to 0 and the other stuff. For example, on a curve, you take 2 points, the difference of the 2 points is something homologous to 0, but the 2 points are different. So integral from A to B may be non-trivial. You know, that type of thing can happen. So the second block, part of the Bloch-Belarusian conjecture say the order of vanishing of this L function with the odd index here at that critical point is the rank of the stuff which is homologous to 0. And then it further says there's something called a height pairing. So this is some lattice, and I have a pairing with values in the real numbers, so I can take the determinant. The determinant computes the coefficient in the Taylor expansion of this function at s equals m up to a rational number factor. And the so-called Bloch-Kato conjectures, which I was vaguely alluding to, will even try to nail down the rational number in some more tricky fashion. And if x is an elliptic curve, it's this conjecture when I equals m equals 1, which is exactly the Birch-Swinnerton-Dyer conjecture. Okay, Birch-Swinnerton-Dyer is the case of this conjecture for these values of the indices. Okay, and then what about that missing rank? I broke the rank up into two parts. That was already, people had some conjecture about that. There's something called the Tate conjecture, which says the order of the pole of this L function at s equals m plus 1 is the rank of that, the other part. Right? The rank I broke into two parts, the part which I cannot see in topology, homologous to 0, and the other part which I see in topology, that rank is the order of the pole. Conjecture. Again, we don't know this conjecture. Even for surfaces, this thing is not known. So lots of stuff is not known. This is really mathematics of the future. That's why I thought this is a good audience to tell you about. What do we know about the conjecture? There's very little evidence actually. One case where we can check is sort of the case for dimension 0. I said Raghunathan's theorem, that's for finite generation. If you want to nail down things more carefully, you need Borel's theorem. Actually, Borel gave beautiful lectures on this in the institute for there was a function at HRI years ago where trees were planted by various people at the new campus and so on. Borel gave a lecture, he explained his proof of this. Those notes are available if people want to see. But that's the case where x is a point. So that case is the theorem of Borel, which generalizes the theorem of Raghunathan. Then there are cases where BB2, Burt-Swinnerton-Dyer, is known in some cases. People have won the Fields Medal for partial progress, so we do know it in a few cases. But what's some of the real evidence? There are explicit calculations of these regulators and heights using the computer. And in fact, one of the people involved, Grayson, worked with Bloch. Grayson is one of the people who's involved in developing Mathematica. They have Mathematica has all these ways to calculate things to very high precision. Some of that software was developed to do these calculations. And you want to check some two things are equal up to rational number. So you compute both of them using the computer. Using the computer, you divide one by the other. If you got 1.6666237, you say, okay, that looks rational to me. You do computation of that side. Both sides, the numbers before division are some horrible things. Integral of this, determinant of some. There's no reason they should have anything, and suddenly the ratio looks like 1.6666 to 20 decimal. There's got to be an explanation. This can't be coincidence. It's like Ramanujam looked at the tau function and said, tau of something is congruent to 0 mod 641 or something. Those things, there has to be a reason. We don't have the reason today, but maybe you guys will find it tomorrow. Guys and gals. Okay. So, finite generation is not known in... Okay, let me just go ahead then. I think... yeah. The last point is for the fancy people. Conjectures fit well with other conjectures about realization functors for mixed motives. For those who know advanced things on these topics, that's supposed to be a motivation for why it works. Doesn't matter. Once you learn more mathematics, you'll figure out what that is. So what's this got to do with that algebra problem which I stated in the beginning? That's really what I wanted to get to. Let me remind you that an algebraic number is a complex number which is a root of a polynomial equation with integer coefficients. For example, square root of 3 or cos of 2 pi by 17, things like that. These are numbers which are roots of polynomial equations with integer coefficients. They're special complex numbers of some kind. The field of algebraic numbers is denoted Q with a bar on top. Means they come from Q by doing something. One concrete consequence of the Bloch-Beilinson conjectures would say that if you take a polynomial in 3 variables with Q bar coefficients and you take a point on this space X, so the polynomial defines the surface, X is the surface defined by this equation, and the point has algebraic coordinates, then the claim is any polynomial vanishing at ABC is expressible in terms of F, the polynomial I started with, and 2 other polynomials depending on the point. This is exactly the kind of algebra problem I tried to solve for x37 plus y37 minus z37. I'm saying the Bloch-Beilinson conjectures say take any polynomial in 3 variables. Assume it has algebraic coefficients and it defines a non-singular surface. Any polynomial. Take any point on it with algebraic coordinates. My algebra problem always has a solution. That's what the conjecture says. For any polynomial, however high the degree, however complicated. Okay, it's a great statement. What do we know about it? Nothing. We don't know this for a single polynomial. Nothing. Take this particular polynomial. Proof for this. I'm an editor of a good journal in mathematics. I'll happily take your paper tomorrow and publish it, if you can prove this. Slightly less fancy, do it when the point ABC have rational number coordinates. There are infinitely many 4th powers of integers which are sums of 3 4th powers. Unlike cubes, right, there are no cubes which are non-trivial sums of 2 cubes, right? Fermat's last theorem, x cubed plus y cubed plus z cubed has no solution. But all higher degrees, we know there are similar things and all of those equations have infinitely many solutions. x4 plus y4 plus z4 equal to w4 has infinitely many rational solutions. So divide by the w4, write the points. That's an infinite set of points. Check it for those points by hand, by any method. We don't know. Okay, this would be a research paper. You'll get a PhD, I think, if you could manage that. Well, you could probably get a better PhD if you did the other one, but anyway. So here's the theorem. Let ABC be complex numbers not 0 and not all 0 and an plus bn equal to cn, where n is at least 4. N could be 37, for example. Then there exists polynomials g and h such that my algebra problem can be solved with this xn plus yn minus zn as one of the 3, if and only if the triple ABC is proportional to another triple where these A prime, B prime, C prime are algebraic numbers. They are special complex numbers which are roots of a polynomial with integer coefficients. This is necessary and sufficient. This is the theorem. Bloch-Beilinson says this is true for every non-singular surface. 0 examples. But at least here are infinitely many examples of that type. There's no reason this should be true either. This is as unlikely to be right as that one, but it's true. This is a theorem. At that time, Krishna was my PhD student. This paper is a consequence of our work. It appeared in the Annals of Mathematics. Anyway, this is Bloch, Spencer Bloch. Some of you might have seen him in Bombay sometimes. He was my PhD advisor, my teacher. He was most recently in Bombay in March. So he visits India often. This is Beilinson. I don't think he's ever been in a developing country in his life, but whatever. Thank you. I apologize for running over time. It always happens.
So you're welcome to ask any questions if you have or comments.
Somebody have a question? How many dollars will I get if I solve question X? That's a good one. I think you won't need the money. If you solve that, if you make serious progress on one of those things, the money will come to you. You don't have to look for it. Don't worry about it.
Okay, thank you, Srinivas. Thank you again. Thank you. So I dissolve this convocation. Please join us outside for some tea and snacks. Thank you. So for the
students who just graduated, please stay back for group photos.
Yeah, we will be
Thank
doing
you.
some photos in groups on the stage batch by
the
batch.
stage.
So please, students who graduated, please stay.
Okay.